Light is so much stranger than you might think. Sure, it may seem simple enough, traveling around the universe, delivering energy from one place to another. It helps us see. It provides life to plants, and thus to our planet generally. It has a reputation for being very fast. And yet, for a source of energy that has become synonymous with greater understanding, light is surprisingly difficult to understand. Light helps us see other things better, sure, but when scientists tried to look at light itself, it was surprisingly difficult. No, I don't mean that they started staring into any lamps. Please don't do that at home. But experiments in the last 200 years or so have proven that what light appears to be and what light is are actually two different things. For one simple reason. Annoyingly enough, light behaves differently when you're not looking at it compared to when you are. What is the true nature of light? Why is it behaving strangely when we're not looking? And what does it say about how the universe really works? I'm Alex McColgan and you're watching Astrum, and in today's video it's time we try and find out. Let's shed some light on light. Let's begin with the basics. What is light? In the early 1700s, Isaac Newton theorized that light was made up of tiny little particles that he called corpuscles. But in 1801, nearly 100 years later, a man named Thomas Young discovered that light must actually be more wave-like than particle-like. He proved this using an important method known as the double slit experiment. He set up a source of light and shone it through two narrow slits onto a board. Young noticed that rather than getting two bands of light on the other side of the slits, a strange striped pattern was forming. This was known as an interference pattern and was incontrovertible proof that light had been traveling as a wave. Why? Let's talk about waves for a moment. When waves travel, they oscillate up and down. But when two waves try to oscillate the same point in space at the same time, you get something known as interference. Imagine you had a bathtub with a rubber duck sitting on the surface. Two waves reach the duck at once. One wave tries to raise the duck up. At the exact same time, the other wave tries to drop it down. What happens? Provided the waves are of the same magnitude and are perfectly out of phase, they will cancel each other out, and the duck would not move at all. This is called destructive interference. Similarly, if the waves both tried to raise the duck up at the same time, the duck would be raised twice as high. This is known as constructive interference. Because waves tend to expand in a circle, two waves next to each other will start to both constructively and destructively interfere with each other. Here are two waves in water. See these lines? These calmer patches are where the waves are cancelling each other out. This is the effect we see with light travelling through the two slits. As the light from one slit propagates, it cancels out the other wave of light at certain points, creating the interference pattern that Young noticed on the board. So the mystery was solved. Light was a wave and not a particle. Except there is more to this experiment than meets the eye. Let's fast forward another 100 years to 1905. Scientists around this time had become puzzled by something known as the photoelectric effect. It turned out that when you shone a light on a metal surface, electron-like particles were coming off it. This was deduced to be because electrons in the metal were getting knocked off it by the increased energy the light was imparting. Imagine it like a fruit on a tree. If you pull the fruit off the tree, you need to use a certain amount of energy. Once the energy is greater than the strength of the fruit's connection to the branch, the fruit pops off. This was happening with the light and the electrons. Once the light hit an electron and gave it enough energy to pass the threshold, it broke free from the metal. However, what surprised scientists was that if you increased the intensity of the light, they had expected the electrons to be knocked away faster. If you pulled the fruit off the tree harder, it would come off faster. More energy equals more departing kinetic energy. However, this did not appear to be the case. Instead, Increasing the frequency of the light increased the velocity of the departing electrons. The intensity of the light didn't affect the departing electron's velocity at all, but did affect the quantity of electrons being emitted. It was a bit of a puzzler. Albert Einstein was the man who solved the puzzle. He deduced that light must be traveling in little packets of energy, so sending more of them, increasing the frequency, was the only way to increase the energy going to the electrons. He called these packets photons, and later earned a Nobel Prize for his work. Light, it seemed, was more like a particle again. Or both a wave and a particle at once? Of course, even this is not the full picture. To be honest, we aren't completely sure about the full picture even now. Instead, we have more results that are contradictory. Let's go back to the double slit experiment. Armed with the knowledge of photons, physicists once again took a look at the double slit experiment. Experimental techniques had improved in the last 100 years, and it was now possible to emit a single photon of light at a time. So, the double slit experiment was done again. This time, only a single photon would be sent through the slit onto a detector on the far side. When this was done, the detector registered the arrival of the photon at just a single point. So, light was behaving like a particle again. But then, why had it interfered with itself in the previous version of the experiment? Scientists had an idea. They sent through multiple photons, one at a time, and plotted the result on the detector. And this is where the result became really strange. Once again, the detector started seeing the photons arriving at single points, one at a time. But bafflingly, the arriving photons started creating a pattern. It was the interference pattern, the proof that light behaved like a wave. But strangely enough, this was only occurring when a single photon was going through at a time. Somehow, the single photon, which was leaving the detector like a particle and was arriving at its destination as a particle, was apparently in some way traveling through both slits at once, enough to then interfere with itself on the other side like a wave. If light was just a particle, then when it went through the slits, you wouldn't see this pattern. You would only see two blobs of light, one for particles that went through the slit and one for particles that went through the other one. And yet, here was the interference pattern with its multiple lines of light disproving that. Scientists tried to pin light down. They set up the experiment, but this time with two more detectors at the slit, so that scientists could observe whether it was indeed passing through both at the same time. It didn't. But at the same time, it stopped creating an interference pattern on the furthermost detector. And from this, scientists began to realize something. Light cared about being observed. To be clear, it didn't matter whether it was observed by a human eye or a machine. The moment light was interacted with in some way by any particle, which is the only way we can detect light, there's no other way to observe it, it started behaving differently than if it hadn't been detected at all. It was as if light was snapping into focus anytime the universe asked it the question of where exactly it was, when without the scrutiny it appeared to relax into something a little more nebulous. Bizarrely enough, this seems to imply that light actually is more like a wave of probability rather than any discrete particle or wave. Anytime it was asked where it was, it confidently provided a definitive answer. It was at this point on the detector. It was not at any other point. But with no one checking up on it, light seems to be traveling in all directions at once, in accordance with certain probabilities. If you ran the experiment multiple times, you could quantify those probabilities, discovering that it was more likely to be on the bands of the interference pattern and less likely to be in the gaps. But anytime a single photon of light was asked, it gave an answer that was 100% concrete. This is highlighted through something known as the three polarizer paradox. Consider for a moment a pair of polarizing sunglasses. Obviously, these reduce the amount of light that can pass through them, usually by about 50%, depending on the type of lens and the wavelength of light. They work by being formed of thin chains of molecules that run lengthways across the lens. Any light that oscillates in the same orientation as this lens gets absorbed. Any that is perpendicular to the chains can pass through without trouble. The interesting case occurs when a single photon is passed through an orientation that's diagonal to the lens. In this case, you don't get half a photon going through. Apparently, you can't just absorb part of the oscillation that is parallel to the lines and let through the other part that is perpendicular. Instead, the photon snaps into either the one orientation or the other. It either is completely absorbed or passes through entirely, but now with a new perpendicular polarization to match what it would have to have had to have been able to pass through easily. How do we know that the photon wasn't this orientation all along? Because of what happens when you start adding more lenses. When you place a second lens behind the first, you can block out the light entirely, provided the two polarizations are perpendicular to each other. Let's say we rotate the second lens 90 degrees compared to the first one. Any light that gets through the first lens has a 0% chance of getting through the second, like trying to post a letter through a chain-linked fence. As a result, we see only black. But add a third lens and place it at a 45-degree angle between the other two, and bizarrely, light starts making it through all three lenses again. This may seem counterintuitive. How does adding more blockages increase the amount of light that makes it through? But this result actually rules out the possibility that the light has a fixed orientation. It must be snapping into focus at each new lens, rolling a quantum dice each time to see if it was the right orientation all along or not. If it makes it through the first lens, a 50% chance, it only did so because it was oriented perfectly perpendicular to the lens's polarization, which means once it reaches the second, it's coming at it from a polarization that's diagonal. So once again, there's a 50-50 chance that it makes it through. It rolls a quantum dice again, and once again has a 50-50 chance of proceeding. If it gets through this hurdle too, then it again snaps to the new orientation, as if it were that new orientation all along, which it obviously wasn't. Which means that now it's polarized diagonally relative to the third lens, meaning that it now has a final 50% chance of getting through. Of course, some photons do not make it through all three of these probabilistic gauntlets. Only about 12.5% of them make it. But that's more than 0%, which is what was happening previously when you only had two lenses. Light likes to behave in discrete quantities. It is quantum. It seemingly snaps to a discrete value when observed, and honestly, we don't really know why. If you think about a wave, there is no reason why you couldn't simply have half a wave. You could half it again and again an infinite number of times and still have an answer that makes mathematical sense. And yet, it seems that down on a low enough quantum scale, you can't half light past a certain point. You can't have half a photon, or even 1.5 photons. And if you try to do so, the photon instead snaps to one or the other nearest integer based on probabilities, but only when it's asked. Otherwise, it's quite content to exist probabilistically, interfering with itself like a wave as it travels along, before jumping to an answer when later asked exactly where it is. What is going on here? This is still being theorized about. The closest comparison we have to it is something known as harmonics, where on a bounded string, only a certain number of waves can exist. On a guitar string, you can have one wave or two or more, but never a number that isn't a whole number. It seems that light works in the same way. Perhaps something pinches the beginnings and the end of the path light travels down, although what this might be and what mechanisms drive it are unknown as of now. Fundamentally though, perhaps the craziest thing about all of this is that this isn't just about light. Although we focused on light behaving like a wave and behaving probabilistically, all particles of matter do the same. Light is just another form of energy, and energy and matter are linked. Particles of matter, atoms, and even complex molecules have been shown to have wavelengths. Electrons are just as quantifiable and just as driven by probabilities as photons are. We are apparently all driven by probability if you scale things down small enough. So what is everything truly made of? What makes up energy and matter that causes it to behave in the way it does? What is going on under the hood of reality? Why is the universe behaving different when looked at compared to when not? And what does it imply to think that even you are on some level probabilistic? What this all means is anyone's guess. The person who figures it out will be the Einstein of our time. But for now, all we can say is that when it comes to reality, it seems the universe is playing dice. You and the world around you might be a lot less certain than you might have thought. Sometimes when I learn about complex topics in physics, it can get a little bit like I'm listening to people speaking in another language. While Babel, the sponsor of today's video, might not be able to help me with that, they certainly can help if I'm actually listening to people speak in another language. Babel is one of the top language learning apps in the world. I can help you start speaking a new language in just 3 weeks, an activity that can make a big difference. I should know, I met my wife abroad, and speaking in her language was a massive help. Babel teaches you real-world conversations for travel, business, and relationships. Einkaufen gehen. So, if you want to learn a language this summer to really open up the world for you, try out Babel to learn your dankes from your mercis. And you can get 60% off your subscription if you click my link in the description below. Ciao vorbei! Thanks for watching. If you like this video, you'll love this one about the shape of the universe. A big thanks to my patrons and members for your support. If you want to support too and get a host of perks, check the links below. All the best and see you next time.